In the last lecture, I focused on the natural resource coal, which was the backbone on which globally we built the Industrial Revolution. Today I'm going to focus on oil and natural gas, and I want you to come away with a perspective of how and why we use oil and natural gas. What were or are the causes of our modern consumption of oil and also of natural gas? In one of the previous lectures, I showed you this slide, Winston Churchill, World War I, where he made the decision to convert the British naval fleet from coal-fired ships to oil-fired ships. Oil has a higher density than coal. It allowed you to travel farther and faster. It also made you more invisible on the high seas. And Winston Churchill's decision was also the primary reason that Britain at that time became involved with oil production in the Middle East, which is a whole other story that we could tell in a different class. You've seen this in discussion and you've seen this in a previous lecture. Just as a reminder, if we think about U.S. annual energy consumption, and I know I have students in here from countries outside the United States, the pie chart would look different, but the key thing I want you to take away today is that when we think of petroleum, I want you to think oil. And obviously natural gas, I want you to think about the natural gas you might be familiar with cooking on a natural gas stove. Petroleum or oil and natural gas dominate globally the primary energy consumption around the world. There are certainly countries that consume more or less than others, but on average across all countries, petroleum or oil and natural gas dominate primary energy consumption. And in the U.S., the two of these sum to almost 2/3 of all of the energy that humans consume, both the energy that we think of when we actually think about our own human consumption, and also the energy that's physically embedded in all the products and food that we eat. Renewable energy, you can see, is about 11%, and renewable energy is divided among all of these different ways of producing renewable energy. And I'll talk about wind and solar and nuclear in the next lectures. As a reminder, in the United States since World War II, when we ideated the concept of suburbs outside of cities, we can see that primary energy consumption has increased almost year over year, and 2018 was the highest on record. The data have not yet been released for 2019, but they're expected to be consistent with 2018 results. And again, if we look at the histograms on the right-hand side, they are dominated by natural gas and petroleum or oil. If we look globally, we see, as I mentioned, a similar situation. Oil is about 34% or a third of global energy consumption, and natural gas is about 23%. So together, the two, oil plus natural gas, account for more than 50% of global energy consumption. And you can see, as I mentioned in the last lecture, globally, coal is about 28% or slightly less than a third. I showed you in the last lecture, this slide for coal, which ranks number 2, slightly ahead of natural gas. And so again, I don't need you to memorize the data on this slide. All I want you to see is that from an historical perspective, as we go from 1965 until today, we can see the growth of consumption in natural gas and oil and coal. And so one of the challenges we have as a global society when we think about divesting from fossil fuels and replacing all of that primary energy and secondary energy in the form of electricity with renewables is we have to fully replace all of this natural gas, all of this oil, and all of this coal. And it certainly is doable, but it is a challenge. So here's one question for you just to get you primed thinking about how much oil globally we consume around the world. If you have been to a football game at the University of Michigan, or if you have seen the stadium walking past the stadium on Main Street, or you've seen the stadium aerial footage during a football game, you know that Michigan has one of the biggest football stadiums in the entire world. At capacity, approximately 115,000 people fill the football stadium. So here's the statement I have at the top. Imagine the football stadium were empty, and right now we opened up a hose and we started putting oil in at the very bottom of the football field, and we allowed that oil to continue flowing into the football stadium. How long do you think it would take to fill the football stadium based on the amount of oil we consume around the world? The answer is 40 minutes, 40, less than 1 hour. Every 40 minutes, the volume of oil that we consume around the world fills the football stadium, which means that during this lecture today, as you're listening to it, by the end of this lecture, globally, we as a global society will have consumed a volume of oil that is equal to the entire filling of the Michigan football stadium, and then we start to refill that football stadium over and over and over again, 24 hours a day, 365 days a year. A phenomenal volume of oil. And as I'll talk about today, 150 years ago, we essentially consumed zero. So first I want to walk through and explain a little bit about oil, and then I'm going to talk about the geology that dictates how oil forms. And I'm showing you a photograph here that I took at a place called La Brea Tar Pits, L-A-B-R-E-A, La Brea Tar Pits in Los Angeles. And behind the flag here is the museum. If you ever go to Los Angeles, it's a great place to visit. And if they still have this, Tuesdays are typically free, so you don't have to pay admission. But when you walk around the La Brea Tar Pits, what you see are small ponds or lakes that I'm tracing over here with the laser pointer. And you can see these animals here, the mastodons. These are obviously not real. These are fake. But when you look at the water, I want you to see how black the surface of the water is. What you're looking at here is a mixture of water, the same type of water that we drink or shower or bathe with, water plus oil, and also natural gas. And it's 100% natural. This is not man-made. This pond or lake has been here for thousands of years. The evidence indicates for probably 20,000 years since the end of the last ice age. And all of the dark color here is naturally a mixture of water, oil, and natural gas. And if we zoom out now and we look at a satellite image here of the Los Angeles area, so here's Burbank, here's Los Angeles proper, right here, Thousand Oaks, Simi Valley up here to the northwest. If we zoom in, I just want you to, Pacific Ocean is off to the left. If we zoom in to Los Angeles, now Los Angeles proper is on the right side of the map, Beverly Hills and West Hollywood. And if I progressively zoom in, this is now an aerial image, and the pond that I just showed you is the one I'm tracing out here in the lower center part of the photograph. And that pond again is 100% natural. And if you walk up next to the pond, I mentioned that it's a mixture of water, oil, and natural gas. If you look now at the pond, this is the pond in the fall when you've got some leaves on top of it. This bubble that I'm tracing out is natural gas that is bubbling out of this mixture of water plus oil plus natural gas. Natural gas has a lower density than oil and water. And so in that mixture, natural gas, just like you might blow bubbles as a child, the natural gas will buoyantly ascend to the top of the water in the pond. It's being held in here because the surface of the natural gas bubble is coated with oil, but eventually the pressure of natural gas, the force per unit area as it pushes out on the oil, it will pop the bubble, and that natural gas will just evaporate into the atmosphere where it will exist as methane, which is the chemical compound we call natural gas. And again, top left, if you ever go, La Brea Tar Pits is fantastic, as is also the Los Angeles County Museum of Art. Both great places to visit if you're in LA. So why is this area of interest? It's of interest to geologists because it is a clue as to how oil and natural gas form in geological environments. And it also has been extremely important for archaeologists and anthropologists who are interested in excavating animals that got trapped in that lake over the last 20,000 years. Now, because the lake is a mixture of water, oil, and natural gas, the oil and natural gas create a very low oxygen environment. So the partial pressure of oxygen is very low, and that is a very reducing environment. So when animals have gotten trapped and fallen into that lake on the time scale of thousands of years, everything about the animal, including the skin and hair, is perfectly preserved. So I was fortunate enough to take my kids to Los Angeles about a decade ago when they were smaller and a lot sweeter at that time, pre-teenage years. And when you walk around, I say that with love, when you walk around La Brea Tar Pits, you can see a lot of grids like the one I'm tracing out here top right and bottom left. And this is a string here on the bottom left where scientists will excavate literally millimeter by millimeter by millimeter down into this what looks like sludge that is oil and water and natural gas. And they excavate and they pull out fossils. So I took this photograph the day that we visited. This is from Pit 91, so there are many pits on the property. And when you look at the pit, you can see here on the left-hand side by year how many specimens are recovered. And it's been just phenomenal for those scientists because, again, everything that they recover is perfectly preserved, and they are able to extract things like DNA for gene sequencing so they can recreate the ecosystem of this area of California going back tens of thousands of years. So let's fast forward to the late 1800s. Now I want to transition from animals that got trapped in that pond to what first put Los Angeles on the map for European immigrants. And what you're looking at here is a map of a part of Los Angeles with the various highways in blue and other roads in orange. And what's outlined here in this field in red is the Los Angeles City oil field. And in black, those are all dots where historically humans have piped oil out of the subsurface. As of 2011, there was only one active well, and that has since been closed. But I just want you to look at this and see all of these black dots. And I'll show you some historic photographs to give you the visual sense of what Los Angeles was like 120, 130, 140 years ago when there was no Los Angeles as we think of the big city today. And the reason that European immigrants moved to Los Angeles in the latter part of the 1800s was because oil was discovered, and it was at that time, for those immigrants, low-hanging fruit. Now, along with that came displacement of indigenous communities, came a lot of race issues that still are challenges for indigenous communities in Southern California today. So please know that I'm not saying this is right or wrong. I'm simply presenting the historical fact of why European immigrants moved here and displaced indigenous communities to get access to oil. There have been great books and movies written about that. One of my favorite books of all time by Upton Sinclair was written in the early 1920s called Oil. That book was subsequently made into a movie called There Will Be Blood, which stars Daniel Day-Lewis, one of my favorite actors. I strongly recommend reading the book first and then seeing the movie. The book is much better than the movie, but I give a lot of props to the movie. So what is oil and what is natural gas? When I say oil, I'm referring to what we call crude oil that comes out of the ground. The oil that you may be familiar with, cooking oil, is not a product of crude oil. If you've ever put oil into a combustion engine or a lawnmower, that is one component in crude oil. And then with natural gas, I want you to picture a stove that you might have at home or you might have seen somebody use, where the light that you see here is part of the exothermic reaction of the combustion of natural gas. In this case, CH4 or methane plus oxygen liberates energy, and it produces energy in the form of the sun's electromagnetic spectrum, which we see. When we think of crude oil, I want you to picture it as a big soup. Imagine a big bowl of soup with lots and lots and lots of different vegetables in it. Carrots and broccoli and zucchini and cauliflower. Sounds delicious on a cold winter day. But when we think of crude oil, I want you to picture a big soup, and instead of vegetables and fruit in the soup, it has lots of dissolved hydrocarbons. Now, each of these is a molecule in its own box, and each of these is referred to as a hydrocarbon. The carbon is here, the letter C, and the hydro are all of these H's or hydrogen atoms. And hydrocarbons are compounds that are built with carbon as the backbone. So think of carbon as the skeleton, just like you would think of the skeleton that runs from the back of your neck all the way down into your hip bones. And then the hydrogen atoms are bonded with the carbon atom to form these hydrocarbon molecules. The simplest hydrocarbon molecule is methane, and methane is natural gas. And then what happens as hydrocarbons become more complex, nature simply adds additional carbon and hydrogen atoms so that the number of hydrogen and carbon atoms increases from C1 or methane to C2 or ethane, C3 propane, C4 butane, C5 pentane. And so the name here refers to the number of carbon atoms in pentane, and nature can increase the number of carbon atoms almost infinitely so that there can be dozens and dozens and dozens of carbon atoms bonded together with hydrogen atoms. But for this class, I just want you, when we think of crude oil, to picture it as this stew or soup of lots of different hydrocarbon atoms, and the simplest of all is methane or natural gas. So we know that there are places around the world where oil and natural gas naturally come to the surface. I showed you the photograph and talked about La Brea tar pits. Here's an example from off-coast Los Angeles. So here's Los Angeles where we looked a few slides ago. Here in red, I've got the Santa Barbara Channel, which is just offshore of Ventura and Santa Barbara. And if you were to put on scuba gear and go into the Santa Barbara Channel, you can actually find natural oil seeps where there is an oil reservoir, or think of a chamber below the sand at the bottom of the water column, where oil exists, and that oil naturally leaks out into the oceans. And you can visually see this as these heavy oil seeps and oil that ultimately we can see on the surface as these oil slicks. Here on the right-hand side, on the left, is another map. And again, the data points here, don't memorize these. It's just an indication of where there are coal oil seeps off the coast of California. On the right-hand side, if you look at this discoloration that I'm tracing out, this is oil that has naturally seeped out of those oil reservoirs at the bottom of the Santa Barbara Channel. And I have here some historical text from the History Channel, a great, great story about the oil history in the United States, where early explorers realized that there were natural seeps of oil and they could use those for a variety of things, including tanning hides and using it as a local fuel source and a light source at night. There's also evidence that Native Americans, indigenous communities, have used oil seeps in this part of the world going back at least 15,000 years. And so we have evidence going back to the late 1700s of the existence of these types of oil seeps both along the Atlantic coast of the United States and elsewhere. So how does oil form? What actually makes oil, and how is oil a so-called fossil fuel? It's a fossil fuel because oil starts out as plankton. On the right-hand side of the screen, I've got an image taken through a microscope of plankton. And the scale bar here at the bottom is 200 microns, so extremely small relative to the ability of the human eye to resolve. These are living animals within the water column of oceans around the world, as well as lakes and ponds and rivers. And plankton live in what we call the photic zone, which is the upper couple hundred of meters of oceans and other water bodies around the world. Plankton photosynthesize. So in the diagram here, what's happening is plankton have shells composed of carbon and hydrogen, and the plankton source the elements that make up their shells from the ocean water. They source carbon dioxide ultimately from the atmosphere, which exchanges to produce carbon dioxide in the oceans. And then they use energy from the sun in the form of sunlight to stimulate that reaction to grow themselves. Now, plankton have finite lifetimes in the world's water bodies, and what occurs in natural systems, as these plankton die, they fall to the bottom of the water column, and on geologic timescales, at the bottom of the water column, those plankton get mixed in with sand and mud and silt at the bottom of the water to become part of the sediment that you might imagine walking on if you could don scuba gear and walk along the bottoms of the oceans along coastlines around the world. Now, if we look in detail at the skeleton of a plankton, this is what you see on the right-hand side. And again, all I want you to see is that it's formed by a backbone of carbon atoms, which are either singly or double bonded to other carbon atoms, and then it is bonded to hydrogen atoms. So when we use the term fossil fuel to describe oil and natural gas, this is why. Because the oil and natural gas that we know today, that we can use today as an energy resource, originally started out as phytoplankton in the photic zones of the world's oceans, where they used photosynthesis as the form of energy to bond carbon and hydrogen together to grow themselves. Now, when they die, they fall to the bottom of the water column, and they go through a sequence of steps. And I want you to understand how that happens sequentially so that we end up with oil and natural gas. So when we talk about oil and natural gas as fossil fuels that are composed of hydrocarbons, what happens to those phytoplankton is, if we look at the left-hand side of your screen, those phytoplankton fall to the bottom of the water column, which is oxygen poor, so it's a reducing environment. And on geologic timescales, if we look at this image in the center right, which you've seen in a previous lecture when we talked about coal, all of the blue here are rivers carrying sand and silt and mud and ultimately discharging as the Mississippi River, which is shown in the photograph at the bottom that you saw in the last lecture. And all of this discoloration in the lower right is that sand, silt, and mud falling to the bottom of the Gulf of Mexico. Now, as that sand, silt, and mud falls, it's also falling with phytoplankton that fall with it. And on geologic timescales, these phytoplankton that start out here on the left-hand side at the bottom of the water column, on geologic timescales, as more sand, silt, and mud, which geologists refer to as sediment, that's shown here in the brown and the red and the brown, as more sand and silt and mud are buried on top of the sediment that contains the phytoplankton experience a temperature increase. So on the left-hand side at the bottom of the ocean, the phytoplankton, when they eventually hit the ocean floor, they have a temperature of about 5 degrees. And with continued burial under more sediment, the temperature that those phytoplankton experience increases. Now, the black part of the diagram that I'm highlighting here, I want you to picture that as mud that contains this hydrocarbon-rich phytoplankton, the former living phytoplankton that now are fossils. And over time, the temperature continues to increase. So we went from 5 degrees to 15 degrees. Now the phytoplankton have been buried deep enough that they're a temperature of 80 degrees. And at that point, the rock that contains the phytoplankton, it now becomes what geologists refer to as a source rock, and meaning that the rock is the source now of oil, where the oil has formed by the high temperature, in this case 80-degree transformation of the phytoplankton into liquid oil. This is what we mean here by the organic rich mud. Organic rich, the organic is that phytoplankton. And in this case, the mud is referred to as a shale, which is the type of rock that geologists commonly find oil formations in. Now, as the oil as the phytoplankton are buried to deeper depths underneath all of the sediment, they go through what geologists refer to as windows. And the windows, there are 3 of them here that I'm highlighting. Initially, that phytoplankton-rich mud or sediment, it initially transforms to a solid rock that we refer to as kerogen. And I've got a photograph here at the top left where you can literally imagine a rock that is dominated by mud but has enough hydrocarbon in it that if you light it, if you throw a match on it, it will catch on fire and it will burn. So first we have kerogen, and notice on the right-hand side over here we have depth in kilometers, and then we have temperature in degrees Celsius. Completely ignore this column for vitrinite reflectance. And all I want you to know here between depth and temperature is that as that phytoplankton-rich material is progressively buried deeper, it gets hotter because of all of the material on top of it. It first experiences what we call the kerogen window, where it's a solid, and then with increased burial and increased temperature, that solid hydrocarbon kerogen is transformed to liquid oil. And as that liquid oil is continued to be buried deeper and the temperature increases, that liquid oil is converted to methane or natural gas, where all of the hydrocarbons that constitute kerogen and oil are broken down, and when we say natural gas, that would be only methane, 1 carbon and 4 hydrogen atoms bonded together, CH4. So notice we go from kerogen to oil to gas as a function of increasing depth and increasing temperature. In the oil, we have really complex hydrocarbon chains shown here in the middle left. We have gasoline, we have diesel, we have motor oil, we have plastic. And then at high temperature and high pressure, or deeper levels of the Earth's crust, we have only methane. So the first 3 I showed you on the previous slides, phytoplankton die and fall to the bottom of the ocean. They're progressively on geologic timescales buried under more and more sand, silt, and mud or sediment. That causes the temperature to increase owing to an increase in pressure. Eventually, that phytoplankton plus the mud in which it's contained is converted to a source rock that is organic rich. And that transformation of kerogen to liquid oil at temperatures above about 60 degrees here, down to about 120 degrees, that transformation that results in liquid oil, that liquid oil is less dense than the surrounding rock and therefore is buoyant, and the schematic on the right-hand side shows you that liquid oil under the influence of gravity attempts to ascend and rise out of the source rock. And this is what forms conventional oil and gas reservoirs around the world, a term I'll come back and define and show you again in future slides. But I just want you to take away the general sequence of events here, going from phytoplankton falling, progressively being heated up, eventually being transformed here to kerogen, which would be a solid rock that contains hydrocarbons, and then being heated up to a temperature where all of those hydrocarbons liquefy and they're buoyant and they want to ascend from the source rock. We refer to that type of geologic system as a conventional reservoir. And that would be the sequence of events to form this conventional reservoir that I've walked through previously. When you think of the reservoir, I'm now showing you an image here, and I'm going to go back one slide, and I want you to picture this source rock here just above the arrow 120 degrees. So imagine we've got this source rock, and it is organic rich. It contains 5%, 10%, 15% hydrocarbons, and those hydrocarbons are now liquid or gas. In a conventional reservoir, shown here schematically, imagine that all of these yellowish peach solid objects, what we refer to here as clasts, those are the actual particles of mud. And in between, among all the particles of mud, everywhere that's dark in the schematic, that is, in this case, liquid oil, but can also be natural gas and can contain water. So now when you look at the diagram, I want you to see that there are two phases within the circle. These clasts, which are the solid mineral particles that make up the rock, and all of the dark material here that's oil. And I want you to see that the oil is everywhere interconnected with itself. One of the hallmarks of a conventional oil or natural gas reservoir is that the rock that contains the oil and or natural gas is porous and permeable. Now, porous refers to porosity, and all of the open space here filled with oil would be the porosity. So it's highly porous or very porous, and the pore spaces are filled, in this case, with oil. And when the pore spaces are interconnected with one another, it is considered permeable. So in this case, this is a schematic representation of a conventional oil and gas reservoir that has high porosity and high permeability. And high permeability is important because that allows geologists to access the oil and extract that oil at relatively low cost. You can think of it like a jelly donut. So imagine you had a nice, fluffy, just-baked jelly donut, and you know that right in the center is all of that jelly, and all of that jelly is in this big pore space, and all of the pore spaces are connected. If you put a straw right into that jelly, you could literally suck that jelly out without eating any of the donut, right? You'd get all the sugar and none of the carbs from the donut itself. This is how geologists extract oil and natural gas from conventional reservoirs, by drilling into this highly porous, highly permeable conventional reservoir and sucking the oil and natural gas out. Now, in oil and natural gas reservoirs, there's variability. There are lots of different details that I'm not going to go into in detail in this class. But all I want you to picture here, you've seen everything on this slide before except the image on the lower left. I just want you to picture that in a conventional reservoir, if we think of it as our jelly donut analogy bottom right, a conventional reservoir is where we've got oil and natural gas, and almost always with some amount of water. And the water is at the bottom because it's the most dense of these three fluids. Oil has the medium density, it sits in the middle, and gas or methane has the lowest density, so it sits on top. And so for a geologist to extract the oil here, all one has to do is drill a pipe into this particular reservoir and just you suck out the oil and natural gas. And the reason that it's inexpensive compared to what I'll call unconventional reservoirs in a few minutes is because there's so much permeability, you can put one pipe in and you can suck out all of this oil and natural gas out of that one pipe. This is what put Los Angeles on the map in the late 1800s, as geologists, as they would know themselves at that time, put pipes in at every one of these black dots to extract the oil from the Los Angeles City oil field. This now in gray are all similar types of oil fields around Southern California in what we call geologically the LA or Los Angeles Basin. And I just show you this to give you a sense that the Los Angeles field is not a unicorn. There are lots and lots and lots of similar oil fields throughout Southern California, including one that underlies Beverly Hills and was mined for oil for decades before it became the hotspot for Hollywood. And I think I showed you these photographs in a previous lecture, but just to give you a sense of what this area looked like, again, remember the jelly donut analogy, and each one of these pipes is a straw that is into the ground, into that jelly donut that's highly porous and highly permeable, sucking the oil out. So this was Hancock Park in the 1920s, this was Venice Beach in the 1930s, and this is what they look like today. And the reason they look like this today is not because there is no more oil to be mined. It's because the social license to mine oil in this part of the United States has disappeared. So the people that live in this part of California, they do not want mining in their own backyard. So what drove the start of the oil consumption boom? So we're going to go back now to the late 1850s to a place called Titusville. Here, the top left is a map of Pennsylvania. Here is Lake Erie, so here's Buffalo and Niagara Falls. New York and New Jersey are off to the right. Here's Delaware and Maryland beneath it. So if we go to Pittsburgh, and north of Pittsburgh is Titusville. And in Titusville, there was a gentleman named Edwin Drake who was the first person on purpose to actually build what we think of as a modern oil drilling infrastructure. And if you look at the image here, this is called the Drake or the Drake number 1, which as best we can tell was the very first oil well in the world drilled into the ground for the purpose of extracting oil to sell it to a buyer. And this is the crude oil that Edwin Drake pumped. Again, this was the jelly donut. He put a pipe into the ground, and gravity helped him by allowing him to just suck the crude oil out. So this is our soup or stew of all of those hydrocarbons, from the simplest hydrocarbon, methane, CH4, to the most complex hydrocarbons where we have very, very, very long chains of carbon atoms bonded together and also bonded with hydrogen. So why did that matter? Who cares? We can put a pipe into the ground in 1859 and out comes a bubbling crude. The game changer for oil was this guy up here on the left, Benjamin Silliman Jr., who was a chemist. This is the year 1855, New Haven, Yale University. And what Benjamin Silliman did is he took this crude oil that was coming out of the ground, and he wanted to figure out what was it composed of, what was in it. It obviously wasn't water, wasn't pineapple juice, wasn't mango juice, wasn't Coca-Cola. He wanted to figure out what was actually inside this crude oil. So he took that crude oil and he did some what we would think of today as very rudimentary chemistry experiments, where he put it in glass jars and then he heated the glass jars at the bottom, and he noticed that he could separate different types of fluids from within that crude oil. And he was able to separate different hydrocarbons that we now think of as gasoline, Vaseline, which is a solid. He made paints, paraffin wax, which he could use to make candles. So what Benjamin Silliman Jr. did was to, in essence, distill the crude oil, or to purify the individual hydrocarbons within crude oil so he could separate them from one another. And this was the game changer. Among the hydrocarbons that he was able to separate from crude oil was kerosene. And by 1870, kerosene, as I indicate here in the text, you could pay about a penny in the money at that time to light your home for an hour. Now, if you go back to 1870 and you Google how people illuminated their homes at night, on average, throughout most of the US and European countries, the favorite choice was whale oil. And whale hunting was horrific. Google that and spend some time going down that rabbit hole, and you'll see why today there's a huge effort not to hunt whales outside of hunting for religious purposes that I'm fully in support of. But Benjamin Silliman Jr. was able to produce kerosene, and all of a sudden you can see lower left, that game changer, which again is 20-some years before Grover Cleveland flipped the switch at the Chicago Exposition in 1893 and showed the world electricity. But kerosene is a liquid, and that liquid allowed you very inexpensively to illuminate your homes at night. And think of what that did. It extended the human day, because now we no longer had to go to sleep as soon as the logs ran out. We no longer had to go to sleep as soon as the sun went down. We could artificially make day as long as we wanted. So that put Titusville on the map. And this is what Titusville looked like in 1871. There literally, in the span of a decade, were thousands of oil wells, each of them piping into the jelly donut and extracting oil. And another rabbit hole to go down would be to look up John Rockefeller, who made his fortune by shipping the oil from these oil fields in western Pennsylvania. Fast forward to today, this is what the modern infrastructure of oil and natural gas wells looks like in the United States and Canada. These are the number of wells per 100 square miles. In total, there are more than 4 million wells, and per 100 square miles, you can see the areas in red that have more than 1,000 wells per 100 square miles. And the only thing I really want you visually to take away is there are oil and natural gas wells essentially throughout almost the entire country. There certainly are fewer here along the Atlantic seaboard, but you see them in Florida, you see them in Mississippi and Alabama and Louisiana and Texas, everywhere up through the breadbasket, up into Alberta in Canada. All over the country we see these wells. So we went from this to this in only 150 years. You can Google this on your own time, but I put this here if you're interested. You can go to this website, fractracker.org, and you can actually search by state, and you can find oil and natural gas wells, if you're interested, anywhere in the country. And in particular, you might be interested to find out how close you live to an oil or natural gas well. We also, in the last half century, have done a significant amount of the development of oil and natural gas offshore. And again, I showed you this slide in a previous lecture. And all I want you to take away here is we used to mine oil and gas right along the coastline. And today we're mining oil and gas in the Gulf of Mexico, where the water can be as deep as 2 or 3 miles. And we have literally built floating cities for this. I put a bunch of dollars down here on the bottom that I don't hold you to for this class. But if you think of the Sears Tower in Chicago, or I think it's now referred to as the Willis Tower, think about the height of that tower or any skyscraper you can imagine anywhere in the world. The floating platform here, Perdido, which was built and is owned by Shell, the Dutch oil and natural gas company, just notice how it compares in terms of its overall height to the Sears Tower. These are massive floating structures out in the world's oceans that are, as we speak, pumping oil and natural gas. So now, how do you find the jelly buried underground? I'm going to switch to unconventional reservoirs, and I want you to focus on the difference between conventional and unconventional. So unconventional reservoirs are those where the mineral clasts, which are the same as the previous slide shown here, there are pore spaces among the mineral clasts. So all of the dark gray or black here is oil. But notice that there's a third phase within this circle, and that is what's referred to here as cement. So think of this as literally glue, or geologists refer to it as cement, that is gluing together the clasts. And importantly, it's causing individual pores of oil to be isolated from other pores. So if you were to put a straw into this pore and extract the oil right here, when you extracted all of that oil, you would never be able to extract this oil or this oil because there's too low permeability. So unconventional oil and gas reservoirs are characterized as having high porosity, where all of the porosity is filled with oil or natural gas, but very low permeability. And the reason that they are more expensive to mine the oil and natural gas from is, as I'll show you, humans have to artificially increase a high permeability environment or produce a high permeability environment. So this is an image you've seen before And remember that in conventional reservoirs, the oil and natural gas are in a high porosity, high permeability environment and easily flow or ascend. Unconventional reservoirs, that does not happen. So how do you actually extract the oil and natural gas? Well, following the United States Civil War in the 1860s, here's a plaque commemorating what's called Robert's torpedo, was the first successful attempt at what we now call fracking. And we now call it hydrofracking because we use water to frack. But I just want you to know that fracking has been around for almost 160 years. And the way that fracking was done is, if you look at the photograph on the right, you would drill an oil well into the subsurface. Now remember, you're not in a jelly donut, you're in an unconventional reservoir with low permeability, high porosity. You would put explosives into the bottom of the well and then you blow it up. And when you blow it up, what early oil and gas pioneers in this part of Pennsylvania realized is that, in quotes down here, you could increase the production or you could increase the recovery of oil by as much as 1,200% within a week of being shot. And being shot means being exploded or blown up. So we've been using fracking for a really long time, but today we do it very differently. Historically, from the 1860s through the 1990s, we would drill vertical wells. So here's the surface, and we would drill into the subsurface. And then explosions would be used that would allow the shock waves to propagate into the rocks surrounding this vertical well. And the shock waves would break the rock apart, and that breaking of the rock is what would create the higher permeability. So we could literally transform a low permeability unconventional reservoir into a high permeability reservoir. What I call up here at the top in quotation marks, enhanced permeability. But we could only do it vertically. This now is how we do hydraulic fracturing today. And I'm going to play the video through and then come back and highlight some components. This is a video that was put together by Brian Ellis, who's a professor in civil and environmental engineering at the University of Michigan. And I just want you to pay attention to the video as it plays through, and then I'll highlight certain parts. Okay, so let me walk back through that now. So we're going to start at the beginning where we've got a rock in the subsurface that's an unconventional reservoir, high porosity, low permeability, and we're going to drill a well starting up here at the top. And as we play it through, without going into the details, just see that a well is drilled, and notice that the well is not 100% vertical. In the 1990s, engineers figured out a way to directionally drill, or what is sometimes referred to as horizontal drilling, but is more appropriately directional drilling, where engineers can drill vertically as deep as 2 or 3 miles, and then they can turn the drill so they can then drill out several miles directionally or horizontally away from the vertical part of the drill. Now, this is literally when I want you to think of it as a straw. Okay, so picture a straw through which you pull water or soda out of a glass. Right? You know you can suck that liquid out of the glass through the straw. So we've got this straw that's now underground, in some cases several miles. And what the engineers then do is they send to the end of the straw explosives, or what are often referred to as perforation guns, and they explode at the end, and the shock wave, notice here, the shock wave radiates energy out radially away from the source of the detonation, and notice now the fractures in the rock. These fractures are enhanced permeability. They are cracks, they are openings. These fractures now have transformed this rock from low permeability to high permeability. Then what engineers do is they send water mixed with sand and chemicals into the subsurface. The sand here are all the small little circular balls that look kind of yellowish or blue on my screen. And there's also what's referred to here as detergent or chemicals. And that's designed so that you reduce the potential for bacteria and fungi and other things to damage the infrastructure. So remember, step one is we drill the well. Step two, we explode a charge at the end of the well. That creates fractures in the rock. Now we pump water in. The water contains the sand, and that sand is a physical entity. It's a rock. So that sand props open, shown here with the red arrows, it props open the fractures or the cracks. And that, when the water is pulled back out of the well, that sand keeps the fractures from compressing back on themselves. So that sand, now that the water is leaving, the sand is left in place, and as a result, the fractures remain open. And now what happens is all of the oil or natural gas that's in the pore spaces, now those pore spaces are connected. It's a permeable environment, and that oil or natural gas, shown in green, is now piped back to the surface. And that's what's shown here. Now we're pulling the oil or natural gas out of the well because we've now connected all the pore spaces to make this source rock permeable, and now we can suck that oil or natural gas out. Now there are lots of potential problems with fracking or hydraulic fracking. One is that that water that comes back to the surface, which is referred to as flowback water, that flowback water, meaning water that has flowed back up, always contains some water that was in the source rock, and that water is always very enriched in dissolved alkali and alkaline earth metals, sodium, potassium, calcium, magnesium, and as such is not potable. So you can't simply use that water as a drinking source for animals or humans. You have to either recycle the water or you have to store the water on, in essence, what are similar to tailings ponds, and then you have to purify or clean that water before you return it to the environment. Or you can take that flowback water to specific sites where it can be injected to great depths within the Earth's crust, where it is thought to remain chemically inert. Among the problems with that is that deep injection has produced earthquakes in places like Texas and Oklahoma and Michigan. So there are a number of challenges with hydraulic fracturing. So if we look here, and this sort of highlights some of them on the bottom left, if we look at this static image, the most recent game changer for oil and gas has been what I call directional drilling, where companies can drill vertically and then they can turn the drill and drill horizontally or directionally away from the vertical stem out to distances of several miles, and then using that mixture of water and sand, They can detonate an explosive which creates a high permeability source rock. They can pump that water and sand in. The sand keeps the fractures open. The water flows back out to the top of the well, and then they can extract the oil and natural gas. Now, again, there are lots of challenges here. In addition to water and sand, they're using different chemicals referred to here as a fracturing fluid. These have been shown to cause contamination in some areas. That wastewater or flowback water has to be treated. There's the potential for contamination of freshwater reservoirs, and I mentioned earthquakes. So certainly a lot of potential for environmental degradation. At the regulatory level, hydraulic fracturing is not regulated by the federal government. It's regulated by individual states. And one of the biggest challenges here is that the technology, which was really invented and perfected in the 90s and early 2000s, led to such a rapid increase in oil and natural gas production that, in my opinion, states were very slow to create regulatory frameworks to minimize the environmental degradation potential because of the royalties or the tax revenue from producing oil and natural gas. So we had this old way of drilling, which was the jelly donut, and this new way of drilling, which has been shown here schematically in a cartoon by James Scherer, as think of it like a tiramisu. You go down vertically a certain distance, and then you go out horizontally. And this has been a game changer. So, big questions you should know. You should be able to understand and describe the differences between a conventional reservoir and an unconventional reservoir. This is what it looks like if you're producing oil and natural gas from unconventional reservoirs. This is an aerial photograph taken out of an airplane in south central Wyoming. And what you're looking at here, I'm tracing out, this is a pad, what's referred to by geologists as a pad, a drilling pad. And this is a drill that's drilling a well down about 3 miles deep vertically. And then about 3 miles, and almost like arms on an octopus, the directional wells at the bottom go that way, and that way, and that way, and that way, and then this way, and again that way. And so think of it at the bottom of that well like arms on an octopus, where you can drill out in any number of directions from one drilling pad on the surface. So we go from the old way of drilling on the left-hand side, where you would need a lot of wells that only drill vertically and could only extract oil and natural gas from conventional reservoirs, to the image on the right-hand side for one particular part of an oil and gas area in Texas, where this one well here can drill vertically and drill then directionally. And so you reduce the surface footprint in terms of the total number of wells that you need to drill. I don't pretend that you reduce the environmental impact. In fact, the amount of oil and natural gas production has increased, and therefore it's easy to conclude that hydraulic fracturing in terms of the overall effect on Earth's climate and ecosystem has gotten worse. So if we think about how oil and gas companies have used this, just a few slides here to indicate the growth in drilling. This is a map here where the red again indicates more wells per area. And all I want you to think about is this is a period of almost 60 years. These are the wells drilled hydraulically and fractured. Since 2000, this 10-year period of time, about a quarter of those wells have been drilled in only that 10-year period of time. So again, all I want you to take away here is this was a game changer, and it significantly increased the amount of drilling that oil and natural gas companies did for oil and gas. As a result, the two histograms shown here, the top is oil, the bottom is natural gas. There are two colors in each, and all I want you to see is that as a function of time from 2000 through 2015, the light blue or Carolina blue in the top is oil production from hydraulically fractured wells. The dark blue is from traditional non-hydraulically fractured wells. And what we know now is that hydraulically fractured wells, they are accounting for more than 50% of oil production. And for natural gas on the bottom, it's the same. if we look at the number or the amount of natural gas produced from hydraulically fractured wells, shown here in sort of the lighter orange color, you can see that more than 2/3 or 67% of natural gas production is from hydraulically fractured wells and only 1/3 from non-hydraulically fractured wells. So unconventional reservoirs that are only now accessible because of hydraulic fracturing and directional drilling, those now dominate oil and natural gas production in the United States. And as a result, all of the areas here that I'm outlining in yellow, and you can see elsewhere on the map, these have been areas for exploration for oil and gas in your lifetime that when I was a kid and your parents were a kid and your grandparents were a kid, nobody would think of mining oil or natural gas from Pennsylvania after about 1880, 1890, when conventional drilling there had exhausted those reservoirs. And we see this here for oil and gas production. And again, the colors in the legend up here, top right, I just want you to see that for both gas and for oil, in the lighter colors here, the orangish brown colors, they dominate oil and gas production. And as a result, in your lifetime, this has led to the United States going from importing the majority of oil that we consume to now producing the majority of oil that we consume. So in my lifetime, I can remember a United States shown here in blue. The blue here is for domestic production of oil, and the red is for imported oil from other countries to the United States. And in the mid-1990s, there was what we called the crossover. The United States imported more oil than we produced for consumption, and this reversed about 8 years ago, where we now produce more oil than we import. And for those in the class who are in political science or international relations, this also has led to a lot of concern because historically the majority of the oil that we imported was from Middle Eastern countries such as Saudi Arabia, and that gave the United States a lot of political leverage with those countries. As we consume or we buy less oil from those countries, there's a concern by the State Department and think tanks that that will reduce the leverage the United States has politically on some of those Middle Eastern countries, and it will allow for other countries to start buying more oil from the Middle East and gain more political leverage. And I invite you to chat with me about that or Google that because there are lots of fantastic pieces written about it. It's also allowed the United States, the top is the same graphic. If you look at the bottom, the United States is in this light blue, Russia's in the orange, and Saudi Arabia is in the reds. The United States in your lifetime has become the world's #1 producer combined of oil and natural gas. And the reason the United States today is the #1 combined producer of oil and natural gas, right, where petroleum is oil, is because of hydraulic fracturing and directional drilling. It's because we have giant ships like the one shown here on the top, which allow us to compress or condense natural gas and produce what we call liquefied natural gas and ship it around the world. And you can see that recorded here in terms of U.S. natural gas exports, which have skyrocketed in the last 5 or 6 years. And all of that natural gas is being produced from wells that are hydraulically fractured and directionally drilled into unconventional reservoirs. There also is lots of great material written worldwide about the impact that hydraulic fracturing is having on other political systems and relationships among countries. If you look at the map on the left-hand side, all of the blue are existing pipelines for natural gas. Russia, historically, top right, has been the major supplier of natural gas to most European countries. Russia now is planning pipelines, you can see in the dashed line, that would allow them to ship gas from the Caspian Sea through Turkey, essentially bypassing northern European countries. And this has led to a lot of political challenges among European countries. And again, if that's an interest, I encourage you to Google that. In particular, see the impact it's had on Ukraine. So I'll skip through this one. And again, this is just a screenshot I took a couple of years ago of a newspaper article talking about the role for natural gas and its political influence between Germany and Russia. So back to crude oil, the sort of text up here that's hard to read. Once it's extracted, what do we use it for? So I'm going to play a video now that gives you a sense of what happens to this crude oil such that we use it for a variety of different purposes.
In this video, you will learn how fractional distillation separates crude oil into useful fractions. Crude oil is the term used to describe unprocessed oil. That is oil that has been taken directly out of the ground, either on land or under the sea. It is an exceptionally valuable resource. It provides us with a great number of hydrocarbons, some of which are useful as fuels, and others are used in the manufacture of many different chemicals and even plastics. However, in the raw form as crude oil, it can be a viscous, dark-coloured tar-like consistency, and the different fractions of hydrocarbons must be separated by fractional distillation for them to be useful. Before we understand how fractional distillation works, we should be clear that crude oil is a mixture of hydrocarbons with different chain lengths, some being short molecules and some being very long. Intermolecular forces act between molecules, and the longer the molecule, the greater the intermolecular force. As you can see here, the small molecules have weaker intermolecular forces, and so will require less energy to break them apart and turn them into a gas. They have a lower boiling point. The longer molecules have greater intermolecular forces. More energy is required. A higher temperature will be needed to evaporate these molecules. They have a higher boiling point. Now we understand how chain length is related to the boiling point of a molecule. Let us look at how this method works. As you can see, crude oil is heated up to a high temperature outside of the fractionating column. The hot crude oil, now mostly in vapour form, is pumped into the column. The column has a heat gradient and is very hot at the bottom, going cooler as we move up to the top. Even at the very bottom of the column, where the temperature is still high, some long chain molecules with high boiling points begin to condense back into a liquid. These are collected at the bottom of the column. The rest of the molecules start to rise up the column, making their way through bubble caps in each tray. The bubble caps slow down the rate of the rising vapour, and eventually the vapours get too cool, condense, and are collected as liquids in the trays. Small molecules have low boiling points, and so condense much higher in the column, where the temperature is cooler still. As you can see, hydrocarbons with similar boiling points are collected in the same tray, and this is why they are known as fractions. They are mixtures of hydrocarbons with similar boiling points. Each fraction has some important uses. Some examples of fractions are petrol, useful as a fuel for cars; naphtha, used in the manufacture of chemicals; kerosene as aircraft fuel; diesel oil, used as fuels for vans, cars and lorries; and bitumen, a mixture of large chain hydrocarbons used to lay roads. Now, at the end of this video, you should understand that crude oil is a mixture of important hydrocarbons, and that fractional distillation is the method used to separate crude oil into useful fractions with similar boiling point. You should understand that small chain molecules are collected at the top of the column since they have lower boiling points, and larger chain molecules are collected further down the column as these have higher boiling points.
Okay, so I don't want to hold you to everything in that video.
That is
I'm
oil.
going to turn the sound off. And what I want you to see here when they talk about fraction, you'll hear a lot fractional distillation. And I mentioned that earlier when we were talking, or I introduced you to the guy Benjamin Silliman Jr. And I'm just going to play this through. And so what I want you to picture happening here is that heated crude oil comes in the bottom, it's all a vapor, or all of the individual hydrocarbons are a vapor or a gas. And from the bottom of the distillation column, it's hot down here and it's cold up here. And you can see that as the temperatures on the right side of the distillation column schematic. And what happens is each of those different hydrocarbons, if it's a vapor and ascends, these little what are called bubble caps, B-U-B-B-L-E, bubble caps, the hydrocarbons that are diesel, meaning that particular length of hydrocarbon chain, they will ascend and they will cool off as they hit the bubble capsule and transform back to a liquid, and then they are piped out, and we call that liquid diesel. Other hydrocarbon molecules keep ascending as a vapor or a gas, and when they hit that bubble cap, the ones that we call kerosene, that have that particular number of carbon and hydrogen atoms, they transform from a vapor to a liquid, and we pull those out. So when we see each of these different fractions, that's what we're looking at. We're looking at all of them were previously part of that stew called crude oil, and now we are actually separating them out. And the way that we separate them out is by the temperature at which they boil, and in reverse, as they go from high temperature to lower temperatures, the temperature at which they condense. So think of this like you might think of dew on grass. During the day, the atmosphere has lots of water dissolved in the atmosphere, and at night, as the temperature drops, that water precipitates as dew on grass, and each one of these bubble caps is like a blade of grass, and each one of these named compounds over here, gas, petrol, naphtha, kerosene, diesel, bitumen, that is where that individual hydrocarbon is precipitating like dew, becoming a liquid, and then we can access it. This is a photograph of an actual distillation column. Another term you might hear if you read this literature or you talk to somebody in the oil and gas industry, they refer to this as cracking, where you're cracking apart different hydrocarbon molecules. And just as a snapshot, not to advocate or say yes, no, right, wrong, I just want you on the right-hand side over here to get a sense of all of the different ways that different fractions of oil are used. And again, on the right, you do not need to memorize this information, but I just write this down here so you can get a sense of the higher temperature compounds have more carbon atoms per hydrocarbon chain, and the lower temperature have lower or fewer carbon atoms per chain. If you look at how we use all of the fractions of oil, about 80% is used for transportation to get from A to B. About 47% is used for gasoline in combustion engine cars. About 23% is diesel fuel for trucks and heating oil. About 10% is jet fuel. So almost 80% is used for transportation. 3%, the very heaviest hydrocarbons, are used for asphalt to build roads. And all of the products that we use that we think of as clothing, etc., they represent a much smaller amount, less than 1%. So why do we use it? I showed you this in a previous lecture. Isooctane, or petrol, is one of the fractions that we can distill from crude oil and add oxygen to, and then spark, combustion, irreversible reaction to carbon dioxide and water, and releases energy, and we can use that energy to drive a piston and move a vehicle. Natural gas, or methane, an identical type of reaction, methane plus oxygen equals CO2 plus water plus energy. And so that oxygen shown here as the red balls and sticks is literally breaking apart the bonds that hold hydrogen and carbon together, 1, 2, 3, 4 hydrogens and 1 carbon. And that energy stored between carbon and hydrogen bonds liberates a phenomenal amount of energy. Now, I mentioned Rockefeller, and we talked about the extraction of oil. I'm just going to give you a sense, and I showed you some schematics of the 4.3 million wells on the surface. I just want to give you a sense now of all of the pipelines right? If we think of the United States having 4+ million wells all over the United States, now look at the pipelines that connect ultimately us to all of these wells. So here the animation is drawing out the states. Orange are crude oil pipelines. So this is oil that's been pulled out of the ground, and there are more than 2.5 million miles of pipeline either at or in most cases below the surface. There are two types of crude oil pipelines. We've got the lines that are called gathering lines that gather the oil coming out of the ground, and then transmission lines that ship that oil to the refineries around the country that use distillation to crack or to distill apart different fractions of oil. We then make stuff at refineries, and the purple are the refined products that are shipped by pipeline. And then we have natural gas pipelines, which are separate from oil. So these natural gas pipelines, they extend around the entire United States. And again, I'm not saying here right or wrong. I just want to give you a sense. If we go back to Titusville, 1859, the first well is put in there. This is the infrastructure that we in the United States have built over the last 160 years. A phenomenal infrastructure, and there also have been significant problems with this and continue to this day, most notably the Dakota Access Pipeline, which is proposed here to run across North Dakota and was proposed to run across lands that are considered sacred and of religious significance and historical significance for indigenous communities. And I am absolutely opposed to, because I think it's unnecessary to ship the oil not only in that area but anywhere else. These are some of the products ultimately that we use oil for that you may not have thought of. And again, it's not a right or wrong or a guilt trip. It's just different things that are made from oil. And you can find lists like this one. This is from the Public Broadcasting System, or PBS. You can find these types of lists or similar. And it's just all the things that you may not have thought of that are used, that are made from oil. And again, these are a statistical, really small number of products when we actually think about the total volume of oil that we extract. So if you were to imagine a world where we would not extract oil for transportation and we only extracted oil to produce these products, the overall impact on Earth's global climate would be close to zero. So again, here's natural gas. If you've got a fleece jacket, right? Fleece jacket, a gallon of crude oil to make the jacket. Natural gas is used to make a lot of textiles. So a lot of what you might think of as spandex. It's also used for space heating, so just different uses. Now, I'm not going to belabor the points on the next couple of slides, except to emphasize something that came through when we talked about metal mining and hard rock mining. If you look on the left-hand side is a histogram, and the numbers here that I'm highlighting are the years left for oil for each of these regions. And again, this is the lifetime left. So you take the amount of oil that we know is in the ground, divide that by the amount of oil we use every year in each region, and you can see that South and Central America here, North America here, Europe and Eurasia, the Middle East, Africa, Asia Pacific, okay? If we all collectively were to continue to extract oil at the rate we currently do, and we took the amount of oil in the ground divided by the annual rate of consumption, these are the years left. The average is about 50 years. And that's shown on the right-hand side. Again, the y-axis is years left. And all I want you to see is outside of the green here for South and Central America, which is actually now declining. Oil is a finite resource. Nature makes it at a very slow rate. Humans consume it at a very high rate, which means that we have the potential to exhaust oil reservoirs, which means that it will eventually go away. And we see the same thing for natural gas. Different regions of the world have longer years left. So the Middle East If only the Middle East consumed the natural gas they produce, they would run out in about 120 years. But if you look at the right, even the amount of gas being produced in the Middle East is dropping. And each of these areas here, you can see a negative trend as a function of time. And the global average for natural gas is also 50 years left. That doesn't mean we'll run out in exactly 50 years, but that means that in the absence of new large discoveries of natural gas, and based on forecasted or predicted rates of consumption, the amount we know exists in the ground today for oil and natural gas is enough to satisfy global consumption for about 50 years. So I want to give you the last part of today's lecture, since I've talked about natural gas, a few minutes to talk about what killed coal. And I'm going to let you read the quote here. If you read different types of media or you listen to certain radio broadcasts or certain television channels, you hear this concept of killing coal, and people hearken back to the great days of the Republican President Ronald Reagan, who denied acid rain until it was almost too late, who also denied that AIDS was something that affected the global population and did not discriminate. That you'll hear people talk about the EPA as the problem, and Barack Obama has been terrible for business and industry. And this is a graphic from an article in the Wall Street Journal a couple of years ago. The data are bottom left from the U.S. Energy Information Administration. And I just want to clue your eyes to the top. This is as a function of time for 1950 for different types of fuels to make electricity, the percent by share. Notice that coal is at the top, and for much of the latter part of the 20th century, coal was give or take 50% of electricity in the United States. But notice if we go back here, starting in the 1980s, we can see coal declining, right? So for decades, coal has been on the decline. And then I'll highlight here, this is in orange natural gas. Natural gas in 1950 was give or take 15% of electricity production. It went up and down and up, a little bit above 20%, back down to about 10%. And notice that in the late 1980s, it started climbing. And if you look at coal, as coal declined, natural gas inclined. And these are data for 2018. Natural gas produced about 35% of our electricity, and coal was about 27% of our electricity. So this was only a couple of years ago. Now, why do you think methane, which is natural gas, might be more favorable for producing electricity? Well, if we go back to a slide we've seen before where we talk about energy density, methane has twice the energy density, more than twice the energy density of coal. And on a per unit basis, if we have coal versus natural gas can produce twice the electricity per unit. So if you look at producing electricity and you wanted to develop a business plan to produce electricity, on the left we've got kilowatt hours per pound of coal and natural gas. And I know we don't think of natural gas as a pound, but just trust me here. The emphasis is that the histogram shows you per unit of natural gas, you can produce twice the amount of electricity. So when you hear things like Obama killed coal, you need to know, and I say this with love, that is completely wrong. It is patently false. You've looked at these data here that I'm showing you now, levelized cost of electricity, and you've worked through these levelized capital costs, operations and maintenance, total system LCOEs. The reason coal is dying is that natural gas is right now far cheaper to produce electricity than is coal. And that's what you see again. Here's from another data source. And all I want you to see is that in my lifetime, coal went up. And then since the 80s, coal has been on the decline. And natural gas sort of hovered between 10 and 20%. And since the 80s, natural gas has been on the rise. The most significant impact is what's shown over here on the right-hand side of the screen. This that I'm circling around, that is the cause, or that has been caused by the combination of directional drilling and hydraulic fracturing that have significantly increased natural gas production in the United States, because natural gas has become much cheaper to produce. If you produce more natural gas at lower costs, we have seen what we call a glut in the natural gas industry, which means there is more natural gas available than there was demand. And so more energy companies, even DTE, are switching over coal-fired power plants to natural gas-fired power plants because it's cheaper. And in terms of blaming Obama for killing coal, here we've got the 4 presidents leading up to Obama: Reagan, Bush Sr., Clinton, Bush Jr., and Obama. And these are the years in office. These are the number of coal miners in West Virginia who lost their jobs during these presidential terms. And you can pause this and look at the numbers. I'll tell you the result. When Ronald Reagan was president, more coal miners in West Virginia lost their jobs than under any president since him, and more than double than the number who lost their jobs during Obama's presidency. So Obama did not kill coal. Coal has been dying for decades. And among the reason coal was dying, here again we've got a timeline on the x-axis, and we have presidents going back to Bush Sr., Clinton, Bush Jr., Obama, and now Trump. The reason coal has been dying, and these colors correspond to the states of Kentucky, Ohio, West Virginia, and the Ohio Valley region, which you can think of as Appalachia. The reason that coal has been dying is A, the price to produce electricity with natural gas is cheaper, but also coal companies have mechanized. So if you look here at this schematic, in blue we've got coal mine employment in West Virginia going back to 1880, and you can see that there were lots of people, more than 100,000 people working in coal mines circa World War I, World War II, and then you can see the number of people working plummeted after World War II. But notice production, which is the red line, production increased. And that's because companies mechanized. They needed fewer people because they used machines with pistons to do the work. And we see this over and over and over again. If you've ever heard somebody say that environmental regulations have killed coal, that is patently false. And here are the data to demonstrate that it's patently false. The blue line is before EPA, and the red line is since EPA. So the EPA was created in the early 1970s. The blue is the period 1928 to 1970. The red is the period 1970 to 2012. And what you're looking at here on the y-axis is the percent change in the mining employment in West Virginia for the 42 years before the EPA and the 42 years after the EPA, and you can see that there is no statistically significant impact of the EPA. So regulations did not kill coal, not in the least. But you hear this all the time, depending on where you get your news. So here we have the leader of the Senate, Mitch McConnell, who vows to fight Obama's war on coal. Now, Obama became president in 2008. So here 2008 is on the histogram at the bottom. But this is the state of Kentucky, where Mitch McConnell is elected as a senator. Notice the jobs in Kentucky. The y-axis are the number of people employed in coal in eastern Kentucky from 1975 to 2019. Notice that we go from 75, 76, 77, 78, 79, 80. It was about 1983, 84 when the jobs started plummeting. If you actually look up Obama's biography, Barack Obama back here, he couldn't have been responsible for these coal mining jobs because Barack Obama wasn't president. Who was president? Ronald Reagan, a Republican. Who was president after Ronald Reagan here? George Bush, a Republican. So I don't say this to tell you the Republican Party is bad, not in the least. I'm a switch voter. I have voted Democrat, I vote Republican, I vote for the candidate who has the values I want in office, and I always vote for a woman if there's somebody on the ballot who also has the values I want in office. What I want you to see here is that if you hear people talk about what has killed coal, and we will hear this going into the 2020 election, coal has been dying for decades, and it's dying purely because of economic reasons that have nothing to do with who's in office. Ronald Reagan back here dismantled environmental regulations, similar to what Trump is doing today, so he made it easier to pollute, and we still saw coal mining jobs decrease. It has nothing to do with politics. It's all about economics. And we see this across the entire country. So now if we look at the national coal mine employment, even after Donald Trump was elected president, the number of coal mining jobs have dropped. So when you see rallies like this when Trump digs coal, Trump doesn't give a fuck about coal. What Trump cares about is pandering to voters. And I will tell you what really frustrates me is my mother was born and raised in West Virginia. I have a lot of family members who were coal miners. And when I see Trump or any political candidate pandering to people because their economies are in shambles, what I don't see Trump doing is providing an economic lifeline, a way to empower people in West Virginia to transition their economy away from what had been their low-hanging fruit to a new economy that doesn't depend on coal. Because if Trump is reelected, I can guarantee you we will not see an increase in coal jobs. No way, no how, ain't gonna happen. And this is the last slide for today to demonstrate why even economists around the world will tell you this is not going to happen. This is an article published in The Guardian just this week, and the quote at the bottom here is from someone they interviewed at Moody's. Moody's, if you're an econ major, you've probably heard of. If you're a Ross major, you've heard of. Moody's is a big economic, I think of it as a think tank or firm, and you can read the text on your own time, but I just want to highlight the graphic on the right, and I want to highlight some of the words. Renewables surpass coal in U.S. energy generation for first time in 130 years. And it is entirely caused by economics. Now, the current pandemic may be accelerating the decline of coal, but if we look, and you look at the gray here that I'm tracing, this is annual U.S. coal consumption. Coal consumption in 2006, it didn't even know about the COVID pandemic of 2020. So again, we see coal is declining. I pointed out in a previous slide, natural gas has inclined and increased, and we see renewables climbing as well. And as you learned this week in Module 8, it is all driven by economics. As someone once said, it's about the economics, stupid. And in this case, that is what has killed coal. End of story. Period. Done.